All right, Hannah, are you ready?
Yeah.
All right, so we are very happy to have Hannah Larson from Stanford, who will tell us about Brill Noether theory over the Hurwitz space.
Great, thank you for the invitation. I'm going to be speaking about some of my work and also joint work with Larson and Isabel Vogt. Historically, algebraic curves were always thought of as existing inside of some projective space. But nowadays, we have a notion of an abstract algebraic curve that exists without reference to a particular embedding. So one of the central questions in the study of algebraic curves is, given some curve, what are all of the ways of realizing that curve inside of projective space? And when we ask this question, it's natural to fix some of the discrete invariants in the problem. So there's R, the dimension of the target projective space, and D, the degree of this map. And then we can ask, what's the geometry of the space of all such maps with these invariants? The data of such a map is equivalent to the data of a degree D line bundle on our curve, together with an R+1 dimensional subspace of the space of global sections. And the sections in this subspace should have no common zeros. So as such, to study this question, I'm going to define WRD to keep track of the degree D line bundles so that H0 of L is at least R+1. So here's a picture. W0D corresponds to the effective divisors on my curve. W1D is the line bundles that can give me a map of my curve to P1, and W2D would give me ways of realizing my curve in the plane. One of the great achievements in the modern study of algebraic curves has been to describe the geometry of this picture when C is a general curve. So first, the dimension of WRD is G minus R+1 times G minus D plus R. I'll denote this by rho, and it's called the Brill Noether number. Implicit in this statement is the claim that if rho is negative, then WRD of C is empty. This was proved by Griffiths and Harris in 1980. And this dimension of WRD is in some sense the expected dimension when we view WRD as a determinantal locus. And this tells us a bit about the local geometry. It tells us that WRD is Cohen-Macaulay, so it has mild singularities. But the main content of part 2 is that WRD is actually smooth away from WR+1D. This is the Giesecke-Petri theorem. And since WR+1D always has codimension at least 2 inside of WRD, we learn that WRD is actually normal. Third, the class of WRD in the Picard variety is a multiple of a power of the theta divisor. This formula was computed independently by Kempf and Kleiman-Laxoff. And knowledge of this class actually tells us how many points are in WRD in the case when it has dimension 0. One nice combinatorial interpretation of this number is that it's the number of ways of filling a tableau that is R+1 by G minus D plus R, so that it's increasing along rows and down columns, and I never repeat a symbol from 1 to G. Next, if rho is positive, then WRD is actually irreducible. This follows from a connectedness result of Fulton and Lazarsfeld for determinantal varieties, together with the normality in part 2. And finally, the universal WRD has a unique irreducible component that dominates the moduli space of curves whenever rho is greater than or equal to 0. When rho is positive, this already follows from the irreducibility in part 4. So the interesting case is when rho equals 0. And here we have a generically finite cover of MG, and we're saying that the monodromy of this cover is transitive. So that's the picture when C is a general curve. But in nature, curves often come to us already equipped with a map to some projective space, say PR0. And the presence of such a map may force our curve to be special and fail the Brill Noether theorem. So a natural question is, how does the presence of this, say, unexpected map to projective space affect the space of maps to other projective spaces? The simplest case of this is when R0 is 1, which is to say we have a curve of fixed gonality. So let's now ask, if I have a general, let's say degree K, genus G cover, C to P1, what can we say about the geometry of WRD? This question is answered by some famous classical works when K is equal to 2 or 3. And in fact, these classical theorems of Clifford and Moroni answer this question for all smooth C. But for higher K, the picture has been a lot less clear. This was the subject of the interest in many authors in the 1990s and early 2000s. And I can summarize their work as saying that WRD has many components of varying dimensions. So they gave some upper bounds on the dimensions of all components. And they also gave some existence results on components of particular dimensions. A real breakthrough on the topic came more recently. In 2016, Nathan Flieger gave the best yet upper bound on the dimension of any component of WRD. And in 2017, Jensen and Ranganathan showed that this bound was sharp. So here's a picture of WRD with its multiple components, and together the work of Flieger and Jensen Ranganathan determines the dimension of the largest component. So in some sense, this is an analog of part 1 of the Brill Noether theorem, the dimension statement. But the question remains, what's going on with all of these other components? One might hope that there's some other discrete invariant in this problem that could explain these multiple components and their varying dimensions. And it turns out there is another discrete invariant here. If I have a curve together with a map to P1, then I can take any line bundle on my curve and I can push it forward to P1, and I'm going to get a vector bundle on P1. And this vector bundle will split as a direct sum of line bundles, say O of E1 through O of EK. And this tuple of integers, E, which I'll call the splitting type, is a new discrete invariant. And so I'll define WE of C to keep track of those line bundles whose push forward has splitting type E or a specialization thereof. Given a splitting type E, it's not hard to recover the associated R and D. So it follows from the definitions that WRD breaks up as a union of splitting loci WE of C over splitting types E that satisfy H naught of that vector bundle on P1 has at least R+1 global sections. So it's natural to instead ask that these splitting loci, WE, satisfy analogs of the Brill Noether theorem. And this is exactly what we found to be true. First, I proved in 2019 that the dimension of WE is equal to its expected dimension viewed as a splitting locus for vector bundles on P1. This quantity here, I'll denote U of E, and concretely, that's equal to the sum over pairs I and J of the max of 0 and EI minus EJ. This dimension statement was also proved independently using tropical techniques by Galen Cook-Powell and Jave Jetson. Part 2 is that WE is smooth away from the splitting loci contained within it for more special splitting types. And the fact that all of these WE are, or all of the open splitting loci are smooth of the expected dimension tells us that the local geometry of these WE reflect the local geometry of the universal splitting loci. Say on a versal deformation space for vector bundles on P1. Part 3 is that WE has class, which is a multiple of a power of the theta divisor. And I proved this formula using intersection theory, in particular some formulas for the classes of splitting loci that I developed. And I was able to show that this number, N of E, depends only on E and not on the genus. So one interpretation of this number, this numerator, as I've written it here, is that it's equal to the number of points in WE of C in the case when it has dimension 0. So unfortunately, the intersection theory formulas I used to prove this are very complicated and nearly impossible to write down. So this number, N of E, remained quite a mystery to me. And then another natural question I think this theorem prompts is, are the splitting loci WE irreducible? We saw that WRD broke up into many components. What's to stop WE from itself having many components? And what distinguishes these questions from the results I have above is that these are questions about the global geometry of WE, whereas these results here are about the local geometry. And we really needed new techniques to address these global questions. And this is the subject of my joint work with Eric Larson and Isabel Vogt. I think we built a much more complete picture of what's happening here. First off, we proved a bit more about the local geometry. We showed that WE is normal and Cohen-Macaulay. Together with the smoothness statement in 2', this actually resolves a conjecture of Eisenbud and Schreier from 2006 about the universal splitting loci. Part 3 is that we gave a combinatorial description of this mystery number, NV. We showed that it's equal to the number of reduced words for a particular element of the affine symmetric group that depends on the splitting type. And reduced words in the affine symmetric group correspond to fillings of certain Young diagrams called K-cores. So another interpretation of this number is the number of K regular fillings of a particular diagram whose shape depends on the splitting type. Then part 4 is we did show that when the dimension is positive, these splitting loci are irreducible. And finally, we proved that the universal WE has a unique irreducible component dominating the Hurwitz space whenever rho prime is greater than or equal to 0. So again, the interesting case is when rho prime is 0, we're proving that this cover has transitive monodromy. So you should think of parts 4' and 5' as saying that really the splitting type is the only other discrete invariant in this problem. So this completes the global statements in analogs of the Brill Noether theorem for splitting loci. And in the last few minutes of the talk, I want to tell you about the main challenge we faced in answering these global questions. So the basic approach that we took, which has been used in many similar problems in the past, is degeneration, which means we're going to try to understand this picture as we specialize our curve to some singular degenerate curve. And we'll try to understand what happens near this special curve X and use that to say something about the general fiber. So for us, we are going to specialize to a chain of G elliptic curves, and we're going to attach these curves to each other so that the difference of any pair of nodes is K torsion. And then we defined WE of X to be the limit line bundles with enough sections at each twist. I'm not going to say precisely what that means, but it's just all of the things that do not violate upper semi-continuity of H naught. So that we get this containment that the limits of line bundles whose push forward has a certain splitting type are always contained within WE of X. And WE of X has a nice combinatorial description. That is intimately related to the affine symmetric group. But this is just a set theoretic containment as I've written it. And that is not enough to tell us what we need, because the pictures could look something like this. So on the left, maybe WE is too large because it has the wrong underlying set. And you'll notice that corresponds to there being a component of the total space of this family that is too small. And then on the right, you can see we still have issues even if WE has the correct underlying set, you could have a problem if the central fiber is non-reduced. And similar challenges to these arise in the proof of the classical Brill Noether theorem. But I want to point out, for those familiar with the Isabel-Harris regeneration theorem, that does not apply here, because WE is not a component of WRD. And even when it is, it has the wrong dimension. So we really needed new ideas to establish a regeneration theorem in this context, which is to say, to prove that these things here don't happen, and we really have this desired equality. And that is the key that allows us to prove our main theorem. We can then access what's happening on the general fiber by studying properties of the special fiber, where we have this nice combinatorial description. So I'll stop here, and I'll be happy to take any questions.
Right. Thanks, Hannah. So maybe I'll clap for everybody. Are there any questions? All right, how about I ask one? So what happens if instead of specifying the map to P1, you specify the map, say, to P2?
I think that's a very interesting question. I'm not sure yet, but I think that's a good question.
When you push forward this family of, I guess, this family of line bundles on the curve to P1, so is that map a smooth map?
The map from C to P1?
Yeah, so this gives us a map from the stack of line, or from the Picard group to the stack of coherent sheaves on P1. Right? Is that a smooth map of stacks?
That's what this is saying.
Okay.
Yes.
Okay.
Yeah, if you unwind this, that's what it should say.
Any other questions? If not, let's thank Hannah again. And again, I'll clap for everybody maybe, so.
If all the speakers from today want to send the slides.
Actually, let me jump in there. What might happen is that it might be better if people want to control their own slides. Instead of sending us the slides, if you put it on your website and send me the link, I can also just attach the link. That might be simpler, so that if you want to change the slides or anything like that, or at some point you decide you don't want to share it, then I won't own your file. Is that okay, Dimitri, Hannah, Pierrick?
Yeah, that's okay.
Okay. So if you just send me the link, then I can add the link to the website and then everybody can access it. All right, thanks. All right, so thank you everybody for coming and everybody for giving beautiful talks this morning. The next talk will be tomorrow again at 9 a.m. Chicago time with Sasha Kuznetsov.
Thank you, everyone.